So, pre-Thanksgiving, good to see so many people here.
We wouldn't miss this for anything.
Oh, well, you know, it's touching. But I intend to finish off chapter 15 of the book tonight. That's the plan. So, last time I did triple integrals. I did other stuff as well, but I mean, I finished triple integrals, the basics. And I wonder if before I start on, say, 15.5, anyone had any sort of triple integration questions that have not got to do with anything in 15.5, 6, or 7 yet? Anyone sort of got something on their minds about triple integrals? No? So I will proceed then. Okay. Well, there's this section 15.5 which deals with masses and moments, and it's pretty similar to what we did for 2 dimensions, and there's a whole lot of formulas that basically just involve triple integrals. So there's no new theory, just this formulas. It comes up once in a blue moon in my experience in past finals. I have seen it happen, so you kind of need to know it, but since you kind of need to know it for 2 dimensions, I think you should know it for 3 dimensions as well. So the situation is this. We have some sort of solid. It's a region in space, which I guess I'll call D. So it's not just the surface, it's actually a lump. It's a lump of rock, and it has a density at every point, just like in 2 dimensions our little plates had densities. Here it has a density, so it might be made of some heavier stuff here than here. It doesn't have to be the same density throughout. So I'm going to assume that the density at x, y, z inside D, the region D, is delta x, y, z. So if delta is always 1, say, everywhere, then that means that, say, 1 unit of volume weighs, or 1 unit of mass has mass 1 unit of mass. So maybe, I don't know, 1 cubic inch weighs 1 ounce, or if you want to go metric, you can do that as well. So that's what the delta is, and it's allowed to be different. So the mass of the whole thing, you need to know this. So it's the triple integral. You have to add up every little bit of mass. Every little bit of mass. So if I take a little bit here, its density is basically delta xyz, the whole place. And I have to multiply that by its volume to get the mass. And then I have to add them all up. And the triple integral accomplishes adding them all up, not just in a line, but in all 3 directions, 3 dimensions. So that's the mass of an object. Notice that if delta is in fact 1, then the mass is the same as the volume. Remember, the volume of an object, just or of the region, this 3-dimensional region. I'm sorry, it's not that at all. It's just 1 dV. Sometimes the 1 is omitted. So that we looked at last week and found, you know, useful. So the mass and the volume are very similar. They're related. In fact, if delta is 1, then you do just get the volume. All right, so that's the idea of the mass. Fairly straightforward generalization of the 2-dimensional version. Now, we also have these first moments. And unlike in 2 dimensions, these are moments about a plane. So there's a physical interpretation that I could spend a lot of time on, but frankly I need to do cylindrical and spherical coordinates. So I'm going to give you short shrift about this and refer you to a physics book. I am very sorry. However, they are very useful for calculating centers of mass, so I do need to tell you what it is. So the first moment about the YZ plane. So if these are coordinate axes, I'm going to take, this is X, Y, Z. I'm going to take a slice through that plane and ask essentially, how does the mass kind of flip around that plane? It's a very vague notion, but as I said, I'm not going to spend much time on it. This is written as m, y, z, and it's the triple integral of x times the density. Okay, so x is actually the signed distance from that plane. Wherever you are, you just need to know the x-coordinate to see how far you are away. And I say signed because this is not the absolute value of x. If x is negative, that counts as negative. Similarly, we have mxz is the triple integral of y times the density, and mxy is the triple integral of z times the density. Okay, and the reason these are useful, as far as we're concerned, is that they allow you to find the center of mass of the whole body. So this is the set of points m, y, z over m, mxz over m, mxy over m. So you need to find 4 triple integrals, luckily all with the same region. So you'd need to find 4 triple integrals and say, now it looks more confusing than it actually is. This has an x in it. Look at the formula up here. So the x-coordinate has an x in it. This has the y and this has the z. So maybe you want to remember it a different way. Maybe you just want to remember it something like this. X times the density dv over just the density dv, and so on with the y and the z. Okay, so I'm going to do an example of center of mass that I found on an old-ish final later, because it's going to use cylindrical or spherical coordinates. I forget which, and I haven't done those yet. So, right, and now there is some stuff about moments of inertia. Again, I would be staggered to see it, but I'll just give you the formula for the moment of inertia about the x-axis now. So this is now the sort of spinningness of this object around the x-axis. That's more words, spinningness, but that's the best I'm going to do at the moment. So this time you really do take the square of the distance from the x-axis. So that's going to be y squared plus z squared, right? After all, if no matter where you are on the x-axis, if you want to know the distance to that axis, and you happen to be at this point x, y, z, you form a little triangle. This is z, this is y. So this distance d equals square root y squared plus z squared. So that's the distance from the x-axis times the density. Dist from x-axis. And then the other formulas are very similar. y, I'm not going to write it out. iz, iy, of course, has x squared plus z squared, so no y there. iz has x squared plus y squared. Okay, so I've never seen an exam question on moments of inertia, but I haven't necessarily looked at all of them very carefully. Again, there's no comma here. The reason why I don't see problems very often about this is that there's 4 triple integrals to do for this. So it's a lot. It's a lot. They better be easy if you have to do 4. Okay? Also, it's not a physics course, but if you take physics, you probably have to do something like that. All right, so I'm going to come back and do a center of mass question. I'm not going to do a moment of inertia question, but I'm going to move on to the next section unless there are any questions about what I've said so far. You could hear a pin drop. But I'll take that to mean there are no questions. Fair enough. Now, something I have a lot to say about. 2 other coordinate systems for 3 dimensions. You remember how in 2 dimensions we had polar coordinates? Well, here there's like half polar coordinates and full polar coordinates. We actually have 3 dimensions, so we can go the whole hog or we can just do halfway. So let's start with the halfway, which is called cylindrical coordinates. Okay, so the idea of cylindrical coordinates is pretty straightforward. You use polar coordinates on the xy only, but keep the z. So if you want to tell someone how to find a point in space using just Cartesian coordinates, you say, okay, this time I'm thinking of this as x, and this is y, and this is z. You say, go a certain distance along the x, then a certain distance on the y, then a certain distance up along the z. And that will get you to x, y, z. But the alternative is you could use polar coordinates to get to that point first, which would mean you go an angle of theta in the xy plane. You sort of orient yourself that way. Then you walk a distance r, and then you go up z. Okay, so basically, instead of x, y, z, you use r cosine theta, r sine theta, and keep z. So x is r cosine theta, y is r sine theta, but z is z. Now you might point out it's become quite special. So you hope that you have some sort of cylindrical symmetry or something like that around the z-axis. This would be totally not suited if you were trying to take a volume that looked like a cylinder around, say, the x-axis. Then you would really want to make this x somehow. So you'd want x and then r cosine theta, r sine theta. That would still be cylindrical coordinates, and it's really not very difficult, but I think that in this course, generally, if you're going to use cylindrical coordinates, I haven't seen problems where you have to be really tricky and use another axis. But I'm going to throw it out there and say, well, look, z, this is the standard form. Maybe sometimes you have to switch x, y, and z around. You know, if it looked like this, you could always just call x z and flip everything around, as long as you flipped everything from x to z in the problem. And then you would get the correct answer. Maybe you'd have to flip it back at the end if you actually have to do the thing. So anyway, nevertheless, there it is. Now, that's the coordinate change, okay? And it's very similar to polar, so I don't even have much to say about it. You do need to know how to convert dv. Basically, it looks like dz dr d theta, except remember dx dy was not actually dr d theta, it was r dr d theta. So it's sort of like that. Or another common way of writing it is just r dr d theta dz. And again, think of the r as going with the dr. Okay, those are exactly the same thing, but they correspond to different orders of integration. And as you know, you pick the order of integration, it can be quite difficult to switch from one to the other. So let's see when you would use one or when you would use the other. Okay, so if your situation, I'll now call this x, y, and z again. If your situation is that the solid that you're integrating over casts some shadow on the xy plane, which essentially is the same at every cross section. At every cross section, except, or at least when I say the same, I'm thinking that it should look something like this. And then the shadow that it casts maybe I'll shift the axis down. I like the shadow to be in the xy plane. So the idea is that most of the cross sections have that shadow or are contained within the shadow. So what it means is if I were going to integrate and set the thing up like this, dz dx dy, what I would do is say pick a point on the xy plane and go up and see where the low z is and where the high z is. No problem. So that's exactly how you would do it. Maybe I'll call it low with a W, high, like that. So that's exactly the same as the regular old triple integrals that we were doing last week. right? You picked some plane to start with, and then you find for some point, you find where the z is, and then you have to worry about integrating over this region here. Well, we're going to do the same thing as we did, but we're not going to use dx dy. We're going to use r dr d theta, which means that you now have to take the shadow here and use polar coordinates on it as if it were a double integral in polar coordinates. So this is the point r comma theta, here's theta, and here's r. And you have to say, well, for this fixed theta, where is the r in, and where, if you kept on going along that ray, is the r out? So you start this ray here of theta, and you say in, out. And so you want to know where you're in and where you're out. And so that's our integral is going to be r in to r out. And then finally, what you need is the first theta. Theta first. That's the word first, which I didn't write very well. And then whatever the last theta is, that will allow you to cover it. Okay, so I've used first, last, in, out, low, high. They're all the same thing. They're all the same thing. I could have written low, high. I could have written in, out, or first to last. But I wanted the idea that there's some first value and then some last value. A question?
So is theta, how do you know where theta, which of those is theta?
Well, you've just got to look at the region. Oh, which one is the first? Well, theta starts along the x-axis and moves along. So actually, this is the x-axis here. So if I start sweeping out and I hit the region, that's why this is the first angle. And then I keep going until I'm no longer in the region, and then that's the last angle.
So it's not like
It's not what? It is like I have it there. I start along the x-axis, and I go first. Now I've last.
Could you do theta between the y and the line, so between the x and the line?
Can I have?
That you're drawing?
Is theta what? Sorry.
Theta is formed by the angle between the x-axis and the line, but on the picture it's formed between the y-axis.
Oh, that is a very good point. I thank you. This is the theta. Yes, please go back and correct this. Sorry, that was a slip. This is the theta. It's a little confusing because it's the projection of this. There's x, there's y. It's the angle down to the positive x-axis. Here's the positive x-axis. There's the ray. So yes, I mismarked the theta. So theta first and theta last are correct, and this is the correct theta. Thank you for pointing that out. Sorry to be confusing there. All right, the point is z low and z high are functions of r and theta. Maybe. Whereas r in, well, now I have no space. R in is a function of theta, maybe. Could be a constant function of theta, but... And the thetas are just numbers. In radians, probably. Okay, so that's the basic gist of something with a constant shadow where you decide to use cylindrical coordinates. However, there is another direction. But before I do the other order, I guess, maybe I'll just do a simple example.
How could you go another order if you just said that they're dependent on each other? That the second integral is dependent on the first and the third is on the...
Well, if you change the order, of course, then that will change as well, as it does in the x, y, z.
Theta will always have to be first, right?
Not necessarily. Z could be first. That will be the other version that I do. Okay? So notice that we have dz, r, dr, d theta, and technically there's an f in here as well. Okay, so I'll just do an example in this setting. Where is my example? Oh man, anyone? I have the book. I know which one I wanted to do, but I just did not write it down. Okay, this is in 15.6, of course. It's relatively straightforward. it says you have, this is question 20, which for all I know is on the homework, so you may get a free homework question out of me. In which case I hope, sorry? Sorry? Oh, good. Excellent. So they said take the line y equals x and take the line y equals 1. And so you get this nice triangle here where the right angle is actually there. And that's the base of a solid. And the height is given by the plane z equals 2 minus x. So that's actually a slanting down plane. If you kept on going, it would hit the x-axis. So it's a sort of plane like this. It doesn't depend on y, so it's the same. Okay. So the top is not flush with the shadow. It dips down. That's the point. And you're supposed to set up a volume integral, or not just, yeah, a volume integral over there in cylindrical coordinates. So suppose you were going to use cylindrical coordinates. So we have an integral of f dv, and we want to set this up as something dz r dr d theta. All right, maybe I need a little more room with the integrals. So the base is this shadow here. So I'm going to pick a point in the base, and I'm going to say, how high do I have to go? Well, how low do I have to go? 0. Z equals 0. No matter where you are in the base, z equals 0. How high do I have to go? I go until I hit the plane. Z equals 2 minus x. The problem is I can't use x. I have to use what x becomes in polar coordinates. So z is going to go from 0 to 2 minus x. But what is x in polar coordinates? It's right there on the board. So this is x. Okay? That's a really poor x. Given any point in the base, where I start and where I stop in terms of z. But it has to be, for the z, but it has to be in terms of r and theta. Okay, now I just have to describe this region here. So maybe the best thing to do is redraw it in the xy plane, and it's actually over here. There's the base. There's y, and there's x. Now I won't get in trouble with the thetas, because I can see it. So actually, given a theta, so suppose I take a theta, where do I start from r? The answer is 0. But where do I stop? What is this distance? This is the r out that I need. Maybe I'll just redraw it even bigger, because here's theta. This is pi over 4 here, because it's slope 1. And I need this distance, r. That's 1. And this is 1. I should have marked, I didn't mark this in. The problem says this is 1 and this is 1. I'm sorry. I did not mark this in. It's in the textbook. That's the problem. Okay, so this whole length is 1. That length is 1. How do I find r? That's the question, given that data. You actually don't even need that this is pi over 4. You just need that that's theta. If that's theta, what's this angle? Pi over 2 minus theta. So we have to do some geometry here. What's this angle? Theta. Look, it's 90 minus theta, theta. So what can we say about theta, 1, and r? What's the equation? Which trig function is it? Come on, talk to me here. Sine, it's opposite over the hypotenuse. So sine theta is 1 over r, otherwise known as r is cosecant theta. So r starts at 0 and goes up to cosecant theta. finally, what's the first theta that applies? Here's the range of thetas that applies. What's this theta? Pi over 4. What's the last theta? Pi over 2. So we're going to go from pi over 4 up to pi over 2. And that's it. It's sort of tricky. Okay? I haven't done the integral. By the way, when you do the integral, you could put the r over here, but it's sort of unnecessary. You do the z integral first, and you don't need that r. And then you evaluate it, and you'll get some mess of r and theta. Then you can combine this r into it. So it looks a little bit confusing to write dz r dr d theta. You could actually write r dz dr d theta if you want to. But this keeps the r out of the way until you actually need it. That's why it's written like that. Okay? Any questions about that example? So the other attitude says that we're going to fix a z. So we've got some sort of solid, and solid may not have the same sort of shadow. It might even be, say, a sphere or something like that. You could do it in this methodology, in the other methodology, but here's how you do an integral that looks like first r dr d theta and then dz last times our function, or integrating our function. So what we have to do is first fix a z. So I'm going to fix a z and take a big slice. And I've got to do the integral over this slice first. So what I do is for that fixed z, I do a mini polar coordinates on the slice. I have to do a polar coordinates on that slice, which means that I pick a theta, and then I find the r in and the r out. So this is the r in to the r out, but on the slice. So you see, r here will depend on not only the theta, but also the z, because it might be different. For a different slice down here, the r might be bigger. And we'll see an example of that very shortly. So then you have the theta beginning, theta out, whatever you want to call it, and that depends on z. Maybe different heights have different slices, although in this picture, the way it is drawn, actually it wouldn't even depend on d. It would be always from 0 to pi over 2. But of course, the thing could be different. It could be shaped more irregularly, and then the theta could be different. And then this is finally the z in to the z out, whatever the first slice is up to whatever the last slice is, and these are just numbers. So you see, they still have the correct dependencies. They're different dependencies on the than the other order, but you can never have anything other than numbers here, functions of, say, the first or the outermost variable here, and then this can be functions of the other two. That's how these things have to be at most. All right, so that's the other method, or at least the reverse order. And so I believe I have an example here. So this comes from problem set 8, or the review session set 8, and it's question 3a. And it itself comes from a quiz from Spring 04. All right, so here it is. It says, let D be the region inside the sphere. They even tell you it's a sphere, although you're supposed to know it. X squared plus y squared plus z squared equals 2. And outside the cylinder, x squared plus y squared equals 1. And the question is, you have, you also have a function, f of x, y, z is equal to z x squared plus y squared. And the question is to find, well, it says first of all set up this integral in cylindrical coordinates. Okay, so first of all, let's look at what the region is. We have a sphere, of radius root 2. And inside this, a cylinder in the xy, well, a circle in the xy plane, but the axis is the z plane. And so it's the volume of revolution of this. So it's a bead. It's a bead with a thick hole, because we want it inside the sphere but outside the cylinder, so we cannot take the inside of the cylinder. So you see how this is a bead. That's it. It's just the outside of that. Okay? Does that make sense? You don't believe it? You all believe it? Okay. So, if we just wanted the volume of this, we could do a straightforward math 1/4 style disks or cylindrical shells type method. But we don't just want the volume. We want to integrate this function, which is different for every point on this. So we're going to have to use triple integrals. There's no way to get around it. It's not just the dv. So what I propose to do is actually use both methods just to demonstrate. See? You want to see them both? I will show them both. See, actually you can do it either order. So let's try first the first method that I said, which says that look at the shadow. Okay, so what is the shadow? The shadow looks like this. It is inside the circle of radius root 2, but outside the circle of radius 1, because that's the cylinder. So the shadow looks like this. And so for any point in the shadow, we actually have to go up to the sphere and down to the sphere. It's fairly straightforward. The cylinder doesn't come into it. In fact, the reason the cylinder doesn't come into it is because actually for every point in here, the vertical line is outside the cylinder. This is a very cylindrically symmetric problem. And so cylindrical coordinates in the z direction are ideal. So the point is that the z value goes down from there and up to here. The question is, how high is it? How high is it? And in order to see it, the point is we have this point here, distance r, and this is 2. Root 2, sorry, because that's the radius of the sphere. So we're only going r out, and you'll see that it doesn't matter if you go from r and go up there or there. I'm going along the y-axis, but that doesn't really matter. The whole problem, as I said, is symmetric around the z-axis rotationally. So if I go out to r and then I go up, the question is, how high is this? Well, you just use Pythagoras. It's that squared minus r squared, so it's 2 minus r squared square root. So that's this z here. And this one is minus the same quantity. So the integral we want is equal to. So first, well, we've got to convert f. We're going to use cylindrical coordinates. So let's take an aside here and look at if the z weren't there, what's x squared plus y squared in polar coordinates? R squared. So this is z times r squared. So that is the integrand up here. Z r squared dz r dr d theta. Okay, so I've just mentioned that no matter what theta is, z goes from minus root 2 minus r squared up to plus. Not root 2, just 2. It's root 2 minus r squared. Quantity 2 minus r squared. So as written. Bless you. Now, what about the r itself? Where does it start? Given any angle theta, actually it doesn't really matter because of the symmetry. R goes in at 1 and out at root 2. So it doesn't depend on the theta. As for the theta, Well, clearly any angle is good here. So we've got to go all the way from 0 to 2 pi. That's the integral. Okay, so actually the theta and the r parts are fairly easy. It's the z part that was a little bit tricky. Okay, you needed to use some geometry there.
Does the radius go to the edge of the inside circle or to the center?
Well, okay, so to do the z part, you have to take a point in the middle, anywhere in the middle. Decide what call the r and the theta, although here the theta doesn't matter. So you take the r and you work out how high the z is. Once you've done that, so you could mark this in. Okay, then you worry about what's the complete range of r's that I need for any individual theta. So now you take a ray theta and you say what's the first r and what's the last r. And then no matter what theta is, by the symmetry it goes from 1 to root 2. Then you worry about what the thetas you need are, which are all of them. Okay, so the first r is in the middle, and then Alright, so now let's actually do the integral. This is part easy. It's just one setup to evaluate the integral. It's not so bad. This r squared is a constant, so you're just integrating z dz for the first integral. So we go from 0 to 2 pi, 1 to root 2. We have from z, the integral of z is z squared over 2, and we're going to evaluate that between negative 2 minus r squared up to positive 2 minus r squared. Then over here we have an r squared and an r, so you've got times r cubed dr d theta. Now let's plug it in and do the evaluation. 0 to 2 pi, 1 to root 2. Okay, so these square roots are going to go away. You're going to get 2 minus r squared over 2 minus the same quantity. Okay, so I plug in, wait, is that correct? No, it's not correct. It is not correct. How is it not correct? Did I even work this out? I worked it out wrong. That's funny. It's much easier than I thought it was. Let's just do it. Wait, is it above the... Nope. That's it. Ha! Okay, I'll tell you why I said ha in a few seconds. So I plug in the other one, and because of the square, r cubed dr d theta. So that actually cancels that out. And this is 0. And now the integral is just 0. That's pretty dumb. They should have just done the part above the xy axis. You see, the deal is this is actually an odd function in z. It's an odd function in z. So because the region is completely symmetric about the xy plane, so if you reverse z and minus z, this integral has got to be 0. That's really dumb. Damn. When I did it, I only did the top half of it. That's what it seems like I did. I didn't check the answer. I didn't have the answer. It's the same answer and it wasn't 0. Okay, let's try the other way. And again, I must have screwed this up. Here's the bead that I'm interested in. Must have screwed it up on my own working. Okay, now I'm going to fix my z. Instead of doing this shadow method, I'm going to fix a particular z, and I'm going to take a slice out of this. And I'm going to ask you, what does the slice look like? Well, it will also be an annulus. The interior is going to be 1. However, because it's the cylinder, but the exterior radius need not be 1. In fact, it won't be 1. What will it be? Well, here's my z distance. This is root 2. So the interior will be, by Pythagoras' theorem, this radius here is 2 minus z squared, quantity square root. Very similar to the other computation. So this is root 2 minus z squared. Okay, so my conclusion is that for any height z, I need r to go between 1 and that quantity in order to cover the slice. And theta still has to do the full 0 to 2 pi. So what I'm trying to claim is that my integral f dv over the region is equal to, so first f is still what it used to be, namely z r squared, but now I'm going to do r dr d theta and dz. I've reversed the order of the thing. So the r, I'm saying, goes from 1 to root 2 minus z squared. And the theta still goes from 0 to 2 pi. And now we just have to decide what's the first z and what's the last z. Well, here it is again, the bead, once more, the venerable bead. Here it goes. This is 1. This radius is root 2. So how high is the maximum height? If this is root 2, and that's 1, and this is right angle, it's 1. And so this is also 1. So z is going to go from minus 1 to 1.
If it goes from minus 1 and not from 0, don't you need to change now the second integral?
So the question is, doesn't that screw this up, you mean?
Yeah, now you...
Well, it doesn't really, because you're squaring z.
Okay.
So this actually works for negative z as well. But it's a good thing to check that the reality, the reality check works. All right? So does everyone see how I got that? Okay, so let's just make sure that this gives us 0. I'm a little bit nervous about this. I got to integrate r cubed. So there's still a z. And if you integrate r cubed, you get r to the 4th over 4. From 1 to root 2 minus z squared. And then we'll still have a dr d theta. No, d theta dz is what's left. So this is the integral from minus 1 to 1, integral from 0 to 2 pi, z. When you take the 4th power, there's the 4 on the bottom. When you take the 4th power, you actually get 2 minus z squared all squared. Okay. Right, the 4th power of a square root is just the square. So let's pull the 4th out. The theta part is very straightforward because nothing depends on theta. So I'll just pull it in like this, and then I'll have z outside of 2 minus z squared all squared. So that's 4 minus 4z to the 4th. No, 4.
Yeah, that's minus.
Where is the minus 1/4? There is a minus 1/4. Dang and blast it. Got to plug in the 1. Man. Okay. It goes through. What? Huh? He? Ooh, ooh. Z is like that. How about that? Have I finally got it right?
No, that should be 4.
Oh, crap dog. It's Z. This is what I get for doing too many things at once. Is that right?
Yes.
But that's not in the square.
Yeah, it's in the front.
That's just bad writing. Okay. Thank you. It's harder to do it on the blackboard than it is on paper. Okay, so I still have the z. I pull out the 4, and then I'm going to expand this mess, and I'm going to get 4 minus 4z squared plus z to the 4th minus 1 dz. Now the theta is just a 2 pi. So this is 2 pi over 4 times the integral from minus 1 to 1 of 4z minus 4z cubed. Actually, I can take the 4 minus 1 and write this as 3z minus 4z cubed plus z to the 5th dz. Okay. Cancel that out if you like. This is going to be 0. Integrate it, you get z squared, something z fourth, z sixth, and when you put in 1 and minus 1, they're just going to cancel out. So thank goodness it is 0. And somehow I just got it wrong twice when I did it. But that's because I only did it from 0 up. I only did the top half of the thing. So as an interesting exercise, try this. Change this to 0 to 1. So that corresponds to the top half of the bead. Okay? Now it's not going to cancel out. See if that integral is the same as what you would get if you saw this thing through, but going from 0 up to root 2 minus r squared. Because that would be the first z that you need to do. And they should come out with the same answer. You actually have to do the integral. Okay, so I leave that to you as an exercise. It's not it's a little exercise. Okay. No. It was 2 pi over 4. And I was trying to cancel this out down to pi over 2, but you know what? It doesn't matter because it's 0 anyway. Okay, but I tell you that that's just a fluke, and I think that you can't count on these things always being 0, obviously. All right. Cylindrical coordinates is sort of half polar. It's half polar because there's only one angle. We left the z. However, we can go full polar and call it spherical. Okay, so what does that mean? We're going to use 2 angles. Spherical coordinates. 2 angles. Okay, so I want to describe a point in space. So the first thing I'm going to tell you is how far it is from the origin. So I'm going to call this rho. It's a Greek letter rho. It looks like a P sort of, but it's an R in Greek, so it's like a radius. Okay, so that will orient us on how far we are away from the center of whatever our coordinate system is. Now, I need to tell you how to find a certain point in space. I've told you what shell it lies on. Now, the next thing I have to tell you is, so here's my point in space. I have to tell you what angle to go down from the positive z-axis. All good positive z-axes go through a word. Okay, so here's my point. What I want to do is go down an angle of theta, of phi. That's called phi. Okay, so if you're at the North Pole, phi is 0. If you're somewhere on the equator, phi is pi over 2. Some people say phi. I often say phi. I reserve the right to say phi or phi, but not fo or fun. Okay, so what we're going to do is we're going to say, okay, how far do you have to dip down? So what I think of is I always sort of, think or put my hand up, and that's 0, and then pi over 2 pi. So the phi has to be between 0 and pi. Or p. No, pi. Greeks actually call this p. But that would be really confusing. Okay, so if you get to the South Pole, so this is the North Pole, and this is the South Pole, you cannot go past pi. Then you start wrapping around the Earth. So this is related very much to the line of latitude. But it's only like a latitude. The problem with it not actually being a latitude is if it were a latitude, then this would be 0 latitude, this would be like pi over 2 latitude, and this would be pi. Whereas it's not, right? This is the 0, and then they sort of increase. So it's not quite the same thing, but it's like a latitude line. Okay, so that's the phi. So actually, once I tell you what the phi is and what the rho is, you now know what the sort of size of the sphere you're working on. And if you know the phi, then that kind of restricts your information as to where you are along one line of latitude. So you now know the line of latitude. To nail down the position, you now need essentially a longitude line. So you need to know what angle you are around here. And if this happens to be the x-axis here, which is an unusual place for me to draw it, but it could just be there, and then this is the theta. So theta is between 0 and 2 pi, as it was before. And this is just sort of like how far around you are, i.e. like a longitude. So it tells you where around from 0 to 2 pi, the revolution. Okay? So that's the order that I'd like you to think about it. Rho, then phi or phi, and then theta. And that's the most common way of writing it. So we're going to be using rho, phi, and theta. Now we're going to need some coordinate transformations. Now in order to do that, it's not so bad as it looks. First of all, let's set it up like this. So we've got some point in space. That's the point we want to describe. Okay, so we've got our rho. I'm going to drop a perpendicular to the xy plane. I'm going to call this r. That's like the r in cylindrical coordinates. Now I'm not going to use that r and the end result, but I'm going to use it to do some computations first. So the first thing to notice is that here is the actual theta, as it was in cylindrical coordinates. And then this angle here is the phi. I'm going to try to write the rho a little bit different from the phi. I guess the textbook writes the phi with a slash through it. Maybe I'll try to do that, just to distinguish from the rho. My normal phi looks like this, but you see how similar it is to a rho, so maybe I'll just try to write it like that. Okay. Forgive me if I forget. All right. Now, what I need to know is, okay, we have x is r cosine theta, y is r sine theta, and z equals z. Well, that's not going to cut it anymore because I'm not allowed to use z and I'm not allowed to use r. So here is the z length. So if you just look in this right angle triangle here, then this distance here is rho, and this height is z. So the cosine of phi is z over rho. In other words, z is equal to rho cosine phi. But actually, in this triangle, this is r as well. This is all parallel, you see. So that's r, that's r. So r is equal to rho sine phi. And if you plug that into these formulas, in both of them, you get the actual transformation that you need, which is x equals r is rho sine phi, and then cosine theta. Y is rho cosine phi sine theta. But the z is just rho cosine phi. So I said, I don't remember whether I said y correctly or not. The point is that they're both sines, because that's like the r. So it's rho, y is rho sine phi, and hell, I've started writing it the wrong. Man. It's been a long day. I need some sort of Thanksgiving. Okay. This you need to learn. You can either just learn it, or you can learn it as something cosine theta, something sine theta, as it was, and then you have to remember that the something is rho sine phi in both cases, and rho cosine theta is the z. Of course, if you can draw a picture and analyze it, that's great. Practically speaking, in an exam, I would just know this. I would just know it. Okay? I mean, in a pinch, if you weren't sure, you could draw a picture of it. But, you know, it comes up often enough that it's worth just committing to memory. All right. So, first of all,
Can you
yeah.
point out how r is rho sine theta on the diagram?
Sine phi is r over rho. Yeah, r over rho. So r is rho sine phi. But as I said, r is a subsidiary variable. We got rid of it. So x, y, z, none of it remained. We've just got one distance and two angles. All right? So it's very useful for navigating your way around the sphere to have the two angles like that. And it is important that you remember that one of the angles, phi, goes from 0 to pi, and the other angle, theta, goes from 0 to 2 pi. That is important. Now, the only other piece of the puzzle is what is dv? dv was r dr d theta dz, but it's different in polar coordinates. So along with this, I mean in spherical coordinates, so along with this, for reasons which I may explain later after I do Jacobians, not only do you not have an r, you have a squared, or actually a rho squared, and you also have a phi in the form of a sine phi. And then you have d rho, d phi, which I'm not going to write properly, d theta. dv is rho squared sine phi d rho d phi d theta. I did not write that very well, but hopefully you can read it. So these two things together tells you how to change the dv part, and so we now have all the tools we need. However, we still need to look at the general method. So the general method follows the same sort of paradigm as all of these other triple integrals. You fix one coordinate, you see what happens, you fix the next, etc. Okay, let's see what examples I want to do. Well, okay, I guess the general paradigm then is this. You have some region which maybe has some sort of spherical type of symmetry. Okay, what you've got to do, because the order of integration, you're doing a d rho, d phi, d theta. So you've got to fix, okay, you've got to fix your idea of what your phi and your theta are. So what you're going to do is you're going to pick a certain point in space, and we'll look at the fixed theta of that point, and we'll look at the fixed phi of that point, but we don't know what r is. So we picked a ray, basically. So the first thing you do is just pick a ray. So every ray can be described in terms of your theta and your phi. No, I've got the theta in the wrong place again. Here it is. Okay, so then, let's say you're solid. Maybe I'll redraw the solid to look like this. There's the solid. So for every ray, what I'm going to do is work out the first r and the last r. And it will be different for different rays. So, again, I go from r in to r out, but it's no longer r, it's rho. Rho is the three-dimensional radius. Okay, so that's my first integral. Then the second thing to do is to work out what is the complete range of rays given theta. So what you do is you pick a theta, which corresponds to some plane like this, and the planes will sort of shift around like a turbine. And for each theta, you have to work out what is the range of the phi. So you'd have a phi in to phi out. And then finally, you have to work out what's the complete range of thetas in the shadow of this thing if you cast the shadow down to the xy plane.
In this example, what would it be of the theta?
Well, since it's a splodge with no coordinate numbers, I don't know. I mean, it would be like pi over 6 to 5 pi over 6 or something. What you've got to do is take the region and take the shadow on the xy plane. And then once you have, okay, so just to do the theta,
In this case, it's 0 to pi
you
over
take the
4.
shadow, well, I don't know, I mean, what's that angle? Say pi over 6. What's that angle? I don't know, pi over 3.
I thought that the x-axis was tangent to the shadow.
This is the x-axis, this is the y-axis.
Uh,
I don't know what it is because it's such a mess. I didn't really have anything precise. Okay, sorry. But what I would do in general is that you have to find the shadow on the xy plane. And then this is the theta in, and this is the theta out. And of course, you don't really have d rho d phi d theta. We have rho squared sine phi d rho d phi d theta. All right, we better do an example. And the example I want to do is exactly the same as the one we already did. Namely, the bead. Root 2, 1, that region. And we're integrating f dv over this domain D. Now, f, you may recall, was equal to z x squared plus y squared. Now, in order to compute this in polar coordinates, in spherical coordinates, we need to do a little bit of work. So the z, you may recall, is rho cosine of phi. There it is. Now, what about the x squared plus y squared? Well, here the r squared wouldn't hurt to keep it as r squared, provided that we have to realize that r is rho sine phi. So if we plug this in, we get rho cosine phi times rho squared sine squared phi, otherwise known as rho cubed rather, cosine phi sine squared phi. Beautiful. We now know what our integrand is. Now we have to do a little bit of work to find out what's going on with our limits of integration. So this is just the subsidiary column here. Okay, now what we're going to do is take some sort of ray. Again, the theta doesn't matter. It's the same because the whole picture is symmetric about the z-axis. By the way, the z is also a privileged direction in these spherical coordinates because it's the North Pole and the South Pole. There's no East Pole or West Pole. So there are different spherical coordinates. You can change x, y, and z around and do it like that and define phi as the distance from the angle from the x-axis or something like that instead of the z-axis. Again, I can't see this being required in this course. I guess anything's possible, but okay, so I'm going to take this ray here and I'm going to assign this a phi, and sure, there's a theta here, but who cares what that is? It doesn't matter. And I'm going to ask, what is the r that you enter, or the row I should say, in, out? Well, because the situation is symmetric, I may as well just look at this picture. Just project it. So it goes from 1 to root 2. Actually, I've got some ray. It doesn't have to be that one. There it is, a general ray, and that's my phi. And I want to know what is this distance and what is this distance. So maybe I can find some colors over here. I wouldn't hold my breath. Nope. Okay. We got two lengths. I'm going to have to do it bigger. That's the solution. There's 1. Here's root 2, the circle. There's phi. So this length here is rho in. And this length here is rho out. And I need to compute both of those using some geometry. Well, the easiest way to do that is to mark this angle as phi again. Keep drawing it wrong. All right. This is 1. So how do I find rho in? There's rho in. There's 1. What's rho in? What function do I need? What trig function? Sine of phi is 1 over rho in. So rho in is equal to cosecant of phi. All right. What about rho out? How do you find that? It's root 2. Yay, it doesn't matter where we are, it's a circle. All right, so we have determined the rho part. And as you see, it doesn't depend on theta, only phi. So our integral is shaping up like this. Okay, so the f we already computed is rho cubed. I'm just copying this from the other board. Cosine phi sine squared phi. And that is the f. Now the dv part is always rho squared sine phi d rho. No room. D rho d phi d theta. And this is the dv part. Okay, we have just computed that rho starts at cosecant of phi and goes up to root 2. Okay, so what about phi? Come back over to this diagram and ask, okay, phi starts up here, right? I said I always orient the 0 up here. And I go tick, 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 tick. Bang, that's the first phi. This is phi in, that angle. And it goes down, in fact, till we get down to the bottom. So phi out is down there. Okay, phi out. I should have. It's down here. All right. So, okay, the question is, what's phi in? Well, we decided that this is 1, this is root 2, and this is also 1. So what's the angle when you first hit it? So it's pi over 4. By symmetry, we hit pi over 2. Where's phi out? Well, it's not negative. It goes 0, pi over 4, pi over 2, 3 pi over 4. Pi is the highest it can be. Yeah, phi has to be between 0 and pi. It cannot be negative. So phi in is from pi over 4 up to 3 pi over 4. And phi out is 3 pi over 4. And, of course, finally, the theta is very easy. Once again, you have the whole rotation of it. So it's just from 0 to 2 pi. So that's the integral in spherical coordinates.
Can you remember one more time how you guys cosecant?
Well, what I did was I picked a general phi that wasn't just the first one or the last one. I had to actually go inside the region that we're interested in, right? And I took my phi, so I go bang, and I need to work out what's that distance. So I copy the phi over here by using geometry, and I say sine of phi is equal to 1, that's this from the cylinder, over rho. So rho is cosecant phi. Okay, and that's when it goes in. When it goes out is root 2. Okay, so that explains that one. And then for the phi, I had to see pi over 4, 3 pi. And then the theta was everything. All right? So that should work out to be 0 if there's any justice in the world. And the reason it will work out to be 0 is as follows. Watch. I don't even have to do all the integrals. I can see it's going to work. How many sines do we have? What's the power of sine? Sine cubed. Okay, there's also a cosine, that's the derivative of it. So if we did a change of variables, then call, say, sine phi, I don't know, t. So this would be actually a t cubed would be the integral in terms of that. But unfortunately, we've got this cosecant, so forget it. I can't predict it. No, I can't predict it. You actually have to do it and see that it's 0. I'm not going to do that. I'm going to leave it to you. Do it yourself. We should get 0. So actually, the problem said, okay, so now we can see the original quiz problem. It said, there's the integral with that region, that volume, well, the domain, and it said, set up the integral in cylindrical coordinates, part A, part B, set it up in spherical coordinates, part C, use either to compute the integral. Now we went a little bit above and beyond. In part A, we did it 2 different ways in spherical coordinates. Obviously, you only have to pick one of those 2 ways and do it. Okay? You have to do that. If you like, you can tidy it up to be rho to the 5th and there. But you didn't have to do the integral. You have to pick the integral that is the easiest. That's the moral. And those other ones were pretty easy, especially the very first method we did it. We just had this integral, the very interior integral became 0. The second way we did cylindrical, we got a more complicated odd function, but it's still 0. And this would be more of a mess, but certainly doable. Certainly doable. Okay, so basically, though, this is the hardest. So I don't really know which one you should pick in general, but you should pick the one that looks easiest. And if you get stuck on it, give up. Try one of the other ones. You can't do every triple integral in every direction. Sometimes it's just impossible, in fact. We've seen examples of that. All right, so that's that question. Okay, I want to do at least one more example of cylindrical and spherical coordinates. In fact, I want to do a center of mass example. But are there any questions about that? Any more questions? No? You're all happy? Question.
Can you give an example where we switch, for example, d phi and d theta, and then switching them?
I really try to avoid switching it in spherical. I really try to avoid it. Most of the problems are d rho, d phi, d theta. I mean, it's certainly possible. Instead of taking a ray, you can take, say, a fixed theta, take a slice and do a 2-dimensional one, but I can't think of an example. If you have one, I'm happy to do it. Yeah, the ones in the book, I looked at them, they were sort of insipid. They were very insipid. I wasn't very impressed with them. I mean, they don't really show you... Okay, so there's only one example in that book. Well, okay, I guess there's 2 examples where you reverse it, but I think it would be more practical if I did something that I think is more likely to come up. So that explains my choice of doing this problem instead of one of the insipid ones, as I say in the book. All right. So I promised to do a center of mass question. That's what I propose to do, and then move on to the Jacobian stuff. Okay? That's the plan. Here it is. All right. Consider this is from a previous final. So it said consider this region. Root x squared plus y squared is less than or equal to z is less than or equal to root 1 minus x squared minus y squared. Okay, and it said this thing has constant density, and you're supposed to find the center of mass. Find the center of mass of that region. Delta is 1. If it's constant, then it doesn't matter what you take it. because in the formula for center of mass, the constant appears in both the numerator and the denominator, as we shall remind ourselves. Okay, so we need to understand what this region looks like. If z equals root x squared plus y squared, then that would be like z squared equals x squared plus y squared, which is a cone. We've learnt all this before. So this is a cone. So actually z has to be above this cone. And if you think about it, this number is always positive. So you don't even get the negative part of the cone. You're not inside. You're just above there. Well, on the other hand, z has to be less than this quantity. So if you graph z squared equals 1 minus x squared minus y squared, that's a sphere. So it's a sphere of radius 1. So everything's 1. That distance is 1. That's 1. This is 1. Sorry? Okay, so how does it factor in? Well, it's just a sphere with radius 1. If this was a 4, then it would be radius 2. Okay, so it is like an ice cream cone. Right. Sort of. It's a smushy, wide ice cream cone, like a wafer cone. The European ice cream cone. There you go. Now, the question is, what is its center of mass? Well, the first thing we notice is that it ought to be on the z-axis if there's any justice in the world, because the thing is symmetric, but we don't know where on the z-axis. So, let us use spherical coordinates to find this. All right. We have to set up what's going on here. Take a ray. What row do we start and what row do we finish? Things are very nice. The first row is 0 and the last row is 1. We just go up to the sphere. No matter where we are, the row goes from 0 to 1. So always row goes from 0 up to 1. How about the phi? Where does the phi start? Starts at 0. No matter where theta is, it goes up to pi over 4. So phi...
How do you know just like that is pi over 4 and not something else?
Well, I mean, that's a good question. I happen to know that this cone has angle pi over 4 because, first of all, if I look at, say, just in the zy plane, this is the point 1 over root 2, comma 1 over root 2. See, just cover up suppose x equals 0. You get z squared equals y squared, so it's a slope 1 cone. But if there was a different number here, say 4z squared, well, then it would be different. Then it would be the line 2z equals y, as in z equals y over 2, so it would be this, and the slope would be, you'd have to compute that, okay? So phi goes from 0 to pi over 4, regardless of what theta is. That covers the whole thing, and then theta goes from 0 to 2 pi. So actually, in spherical coordinates, that cone is just it's like a cube or a rectangular prism. Nothing depends on anything else. I bet you didn't know when you're eating a European ice cream cone that you're actually eating a rectangular object from a spherical coordinate point of view. All right, so our volume or our mass, which is the same thing, is going to be just the integral of 1 dv over the region D, which is, so 1 is 1, sure, but the dv is just rho. We've got to put in this rho squared sine phi, and then d rho, d phi, d theta. And rho goes from 0 to 1. Phi goes from 0 to pi over 4. And theta all right. This is actually a very simple integral because we can split it all up. Nothing depends on anything else. So we can actually do all three integrals in one go. We could write it as 0 to 2 pi d theta times 0 to pi over 4 sine phi d phi, and then times the integral from 0 to 1 rho squared d rho. How about that? It's just the product of three things. It's not even really iterated. So this is 2 pi times minus cosine phi evaluated between 0 and pi over 4 times rho cubed over 3 evaluated between 0 and 1. So you get 2 pi. Cosine pi over 4 is 1 over root 2. We have a minus outside there, and then we also have to deal with cosine 0, which is 1. So when all's said and done, you get this. And then 1/3. So that's the mass of the object. That's m. So we're going to need that. However, we also need three other integrals. Luckily, two of them are very easy. Let's do the moment about the yz plane. That's the x appropriate one. We do exactly the same integral. Well, I'll just set it up like this. But instead, we need x dv. So we don't have to do any more work in a way. We just have to repeat this 0 to 2 pi, 0 to pi over 4, and 0 to 1. And we'll have still rho squared sine phi d rho d phi d theta. But do you remember what x is in spherical coordinates? You see, we have an x here that we need to change. Rho sine phi cosine theta. Not the inertia, the first moment. The formula for center of mass that I did said we need to find all the first moments. So we need to compute this with an x, a y, and a z. And each one divide by the mass. Yep. But you see, this is not as bad as it looks. It's not as bad as it looks because I'm going to split it all up. Once again, nothing depends on anything else. The theta integral, which used to be just d theta, now has a cosine theta. So watch this. There's nothing up my sleeve here. Why do I say junk? Because this is 0. You can compute this. It's just the integral under a complete revolution of cosine. It's clearly going to be 0. But you can do it by fundamental theorem if you like. Write it as sine theta, 0 to 2 pi. This is 0. Okay, you don't even have to do the other integrals. Pretty nice. It's pretty nice. The same thing happens if you try mxz. Exactly the same thing, but now the integral will be from 0 to 2 pi of sine theta. And this confirms our suspicion that due to the symmetry, there's no x or y coordinates. There's 0. The center of mass has to lie on the z-axis. So I will not expect to find a non-zero answer for mxy. Let's see what I get. This is the integral of z dv. By the way, if you don't believe this, do it. You'll see. But I want you to save a lot of time when you're actually doing it by realizing that you can bust up the integrals and do the easiest integral first when it's 0. This time we're not going to get a 0. Let's see why. We have 0 to 2 pi. We have 0 to pi over 4. We have 0 to 1. And z is equal to rho cosine phi, and there's no theta. So we don't have any of this theta cancelling stuff. So we have rho cosine phi, and then we have our change of variables, rho squared sine phi d rho d phi d theta. Again, we can split up all the integrals. This is the easiest way to do it. So we get a d theta. The phi part looks like this. Integral from 0 to pi over 4. We have a cosine phi and a sine phi. And the rho squared is as it was before, 0 to 1 rho cubed d rho. Okay, well this is again 2 pi. The derivative of sine is cosine. So a substitution is going to give us sine squared phi over 2. Evaluated between 0 and pi over 4. Just double check that. Differentiate this. You get 2 sine phi cosine phi over 2. Yes. And then the other one is a rho cubed still. Wait, it's not the same as before. Before we had rho squared. Now we have rho cubed, so it's rho to the 4th over 4. 0 to 1. And so if you work this out, you get 2 pi. Sine pi over 4 is 1 over root 2. You square it, you get a half. You get 2 pi. We have a half there, and we have another half. And then this will give us a quarter. So I make this pi over 8. All right. So the center of mass is myz over m, mxz over m, mxy over m, which is equal to 0, 0, and then the only interesting one is this quantity, pi over 8, divided by whatever the mass was from the beginning, 2 pi times 1 minus 1 over root 2 times a third. And no doubt you could tidy this up a little bit. Tidy. I don't know, to put the 3...
2 pi times, I see the pi over 8, I see the third, but where did the rest come from? The denominator?
The mass.
Ah, the mass is all these times.
Yeah, the mass is a mess. The mass is a mess. The mass is a mess in this case.
They didn't get it. They didn't get it.
It's not really funny. They probably got it. They just didn't really react. They gave it a miss. Okay. See, they didn't get that either. All right. Any questions about that example? Okay. Jacobians? Yes?
Yes.
Yes. All right. Jacobians. This is the version of substitution that applies to three variables. So we've done substitution in one variable. Let's look at that from a slightly different perspective, and this will show us how to do the Jacobian. So suppose you're doing an integral in just x, and you want to make a substitution in this manner. Let's say x equals t squared. So we're going to do a substitution, x equals t squared. Okay, so what we do is wherever we see an x, we replace it by t squared, and whenever we see the dx, we replace it by 2t dt. And we get a new integral in t-land, which we solve. Now, what does this mean, dx equals 2t dt? One way of seeing it is this. Suppose that this is x, well, maybe I should even put it over here. This is t. So I'm going to mark out even strips for the dt. What happens when I square 2? I get 4. What happens when I square 3? I get 9. How do these strips look when you square them? Well, they spread out more and more. So they're not evenly spaced here. They're evenly spaced here, but they're not over here. I don't know if I have the same number. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so 7 strips equally spaced get expanded In fact, I probably have underwhelmed the amount of expansion. It's just a rough diagram. So what I'm trying to say is that the dx, which is sort of this distance, is not the same. It depends on what the originating t was. And so what this says is the stretch that you take of whatever the dt is for this actually is basically 2 times whatever the t value is. So when t is larger, the stretch is larger. Here, this one gets stretched 4 times as much. So whatever that length is, this is 4, because 2 times 2 is 4. Whereas this one is stretched 6 times as much. So maybe that's not actually drawn very well after all. This is supposed to be 4 times, and this is supposed to be 6 times. So that's a lot of bogus bollocks. Bollocks. So if I'd drawn it properly, that strip and this strip this is 2 squared, which is 4, but this is not actually 3 squared. It's actually, 3 minus a seventh or whatever it is. So, but it's roughly a 3-to-2 ratio. Anyway, I can't squeeze them in. The point being that they get bigger steadily as they go. Okay, so that's what this formula means. When you're doing a definite integral in the t space, the function heights are the same, but the thing is stretched out. It's just the point is it's not stretched out uniformly. It's stretched out more over here than over there. So what happens in 2 dimensions? Let's say in 2 dimensions we have this xy plane here, and we want to find an integral. And we want to change variables so that x becomes g of u comma v and y becomes h of u comma v. So this is a change from xy to new variables u, v. Just like we changed x here to t, function of t. Okay, what we need to do is we need to first of all understand how a little dx dy becomes a du dv, or what the correct change is from that. So here's the way I want to see it. Suppose that you fix a v. So you fix a v. And you draw the graph of x equals, so xy is g of uv, h of uv for different u. So fix v first and allow u to vary. So you're going to get some sort of level sec. So this might be v equals 0. And this might be v equals 1. It depends on what that function is. So as you let u be different, so this is different u. Different u's, but the same v. In order to make this come to life, I wanted to do it in general over there, but maybe what I'll do is just take your coordinates r comma theta. Suppose you fix the theta. So fixed theta. The question is, what does it look like for different r's? For different r's. So I'm fixing theta, and I want to look at what happens when I change r. Well, I get this ray. So that's one level set. So that's theta equals, say, pi over 3. Theta equals pi over 6, etc. Okay, I could also do the same and fix u instead. So maybe that looks like this. So this might be u equals, say, 1, and this might be u equals 0. And this is different v's. Okay, so here, if I fix r and let theta vary, I get a circle. So this is r equals 1. This might be r equals 2. So what was a square? A square in the coordinates actually looks like this. And a square in these coordinates looks like this. It's all distorted. Here it's distorted too. Okay, so with respect to the x and y, everything's very curvy or bent or distorted. But if your world is in u, there's your v-axis and here's your u-axis, right? Of course, then the x and y would be all drugged out as well. So, I mean, this thing is all sort of... Okay. Anyway, you get the idea. Now, what I want to do is I want to work out what is the area of this. Because the dx dy is going to be this area times the du dv. Now, this is all bogus because v equals 0 and v equals 1 is too big. This thing doesn't look anything like a little parallelogram. But as you zoom it in, so if I kind of took this picture and instead got really close, so suppose I took v equals 0 and I took, say, v equals 0.1 or 0.01. And then I did the same thing, and this is u equals 0, and this is u equals, say, 0.2 or something, or 0.02. It doesn't really matter. Now this thing kind of looks like a little parallelogram. It's not exactly, but it's a lot more parallelogram-ish than that big old thing there that's all distorted. Okay, so the question is, what does that parallelogram look like? Well, let's zoom back in on it, draw a bigger picture. I'm not changing that picture, I'm just now zooming in on this section here. So, once I clear the space, this is all going to come together in just a few seconds. This is supposed to be fairly close. So this was v equals 0, v equals 0.01, u equals 0, u equals 0.02. So, okay, so my question is, if you think of it as a parallelogram, what is that length? Well, that tangent vector there, this is where we come back to the vectors. See, we have xy is g of uv, h of uv. So the tangent along the u direction for a fixed tangent in the u direction, you just differentiate dg du, dh du. So that's this vector. And of course, if I multiply it by a du, I actually get the length of this little thing here. So multiply that by a du, and that gives me this length. It gives me this vector. So it's renormalized. It's actually not quite along the curve, but it's very close to the curve. So let's call this vector, I don't know, what am I going to call it? A. So this is A. It's not a unit tangent, it's the tangent times the length. And then I do the same thing for the B, V direction. I have B equals dh du, I'm sorry, dg dv, dh dv times the length dv. All right, so I'm going to approximate this by a parallelogram of sides A and B. Now, what's the area of a parallelogram? Go back to earlier. How do you find it? What do you use? You use a determinant in the cross product sense. AB sine theta, but it's done by a cross product. What you do is you set up a cross product of this vectors with a 0 in the third coordinate, and then you find the k thing. So basically, the area is equal to, you just take the determinant whose rows or columns, as it turns out, in order to be consistent with the general thing, we actually have to take a column vector of A and a column vector of B. So essentially what it works out to be is dg du, dg dv, dh du, dh dv. Now there's some question as to these du's and these dv's. If you see put those in, then you'll have du dv in both places, which is good. That's exactly what you want. So, but I'm just going to shove it outside. And that is called the Jacobian. Actually, this gives you not the correct area, but the signed area, depending on the orientation of those things. So you kind of need the actual, that's a determinant. Now you need an absolute value, which is really ugly. So that's an absolute value here. And this is a determinant. It's unfortunate that the determinant could be negative despite the fact that they look like absolute values. Okay, so this weird matrix is actually an area. It's an area of a parallelogram. That's what it means. And it's a distortion factor, just like here we have different distortion factors depending on where we are. Here we have different distortion factors depending on where we are. In particular, the thing gets more and more distorted as r gets bigger. When r is small, it's almost like a regular little rectangle. But when r is big, it's much wider at the top than it is at the bottom. And so that's why you have an r dr d theta in that case. So let's try to summarize, since time is running short. G is just the same as x, because x was just g, and h is the same as y. So if we let j, for Jacobian, after the dude who discovered it, be dx du, dx dv, dy du, dy dv, and these are all partial. We take that determinant. Remember, that determinant doesn't have to be positive. It could be negative.
X and y instead of
Yeah, because x equals g. The transformation is x is g of uv.
okay, okay.
So, you know, normally you can say, it's like the chain rule or something. There's always these different versions of it, but essentially that's this. So then, given this Jacobian, we have the following. The integral of f of x, y, dx dy, over some region, and that region is described in x, y coordinates, is equal to the integral. First of all, you have to change x to u and v. So this is x of u, v, which I called g before just to avoid confusion, but now I'm just going to call it. So we replace these. And you'd like to write du dv, but instead you have to put the absolute value of that Jacobian that you've computed and then du dv. And that's the change of variables formula. The new coordinates.
Jacobian is in absolute values or in...
Well, okay, the Jacobian is a determinant. The determinant is this times this minus this times this, and it can be negative.
Right.
Okay? But because it represents an area, for this to work properly, you then need to take its absolute value. Okay, so it looks better that way than like with a big absolute value around a determinant, but it's the same thing. Now, the only time this formula is not true, well, I guess x and y have to have derivatives. But if they have derivatives, the only problem can occur if this is 0. If this is 0, it may not work. It is allowed to be 0 occasionally, but just not significantly. And that's a big topic of advanced calculus, which I don't really have, I mean, it's not in this course, but why would you use this? I'll give you an example. Why would you use change of variables in one-dimensional integrals?
I mean, like, why? I mean, I know you can do the transformation, but are you doing it because you wouldn't be able to do it without transforming?
Exactly. Exactly. There are some integrals that you cannot do without transforming because the integral is impossible. But there's another reason. Sometimes you can transform the region into a much simpler region in other coordinates. So you might as well ask, why are we doing, say, polar coordinates? Because polar coordinates is a special example. In fact, I'll just compute the Jacobian for polar in 1 second. Here goes. dx dr, dx d theta, dy dr, dy d theta. Let's just do it. dx dr is cosine theta, dx d theta is r minus r sine theta, dy dr is sine theta, and dy d theta is r cosine theta. Compute this, you get r cosine squared theta minus r sine squared theta. Which is just r. Okay? So what does that mean? What it means is dx dy is equal to the absolute value of this Jacobian, dr d theta. But because the absolute r is positive, this is just r dr d theta. So if you believe this Jacobian stuff, then it gives you the formula that we've already said, which we didn't really prove. Okay, and if you try the same for cylindrical or spherical coordinates in 3 dimensions, it also works. Now, by the way, the 3-dimensional version is just the same, but I don't have time to write it up, alas. I'd rather do some problems. But the 3-dimensional, you'll have squeeze in here a dx dw, a dy dw, and then you'll need a dz du, dz dv, dz dw, okay? So exercise, write it out for 3 dimensions. By the way, what does that 3 by 3 determinant represent? Instead of the area of a parallelogram, it represents the volume of a parallelepiped. Why does it work? Because it is a triple box product. Okay, so that goes back to the geometry that we did much earlier. Now, I better do at least one example. This doesn't take quite as long. Question is, where did I leave the damn thing? Oh, problem set 8, please. Where are you? Here you are. Okay, here goes. This is from the final of Spring 03. It said, let R be the region in the first quadrant of the xy plane bounded by xy equals 1, xy equals 4, and the lines y equals x and y equals 4x. So we better draw it. xy equals 1 is just y equals 1 over x. xy equals 4 looks very similar, but it's a bit higher. Y equals x looks like this, and y equals 4x looks like this. So the region we want is this weird looking thing here. So there's the region, and we're supposed to find this bizarre integral. Root y over x plus root xy dx dy. We're supposed to do this. And it even tells you what transformation you're supposed to use. It says you use x equals u over v, y equals uv. It was very generous of them to tell you the transformation. Okay, if they hadn't given us, what thought process would you do? You would say, oh look, y over x is 1. Y over x is 4. So I kind of want one of the variables to be y over x. Say, I don't know, v. So I might have let v be y over x. And then I would do the same thing and say, oh look, xy is u. So maybe I would do this. xy is something interesting. It goes from 1 to 4. So I'd say, oh, let u be xy, and let v be y over x. So then I can say that u goes from 1 to 4, and v goes from 1 to 4 as well. Now that's not the same transformation as what they've asked for, because if you solve for these two things, say you multiply these things together, you will have uv equals y squared. So you'd have y equals root uv. But I suspect that transformation will work as well. So there's not always one transformation. Anyway, time is running out, so I better do the problem. Okay. So the first thing to do is convert the integral. Root y over x, well, let's just work out y over x. It's uv over u over v, which is v squared. So this is root v squared. What about x times y? Well, multiply these together and you get u squared. So it's plus root u squared. Okay, it's very tempting to do 3 different things. One, just to write down r here, but you really should actually not. It's tempting to write du dv, but you shouldn't. And
You shouldn't write u dv?
no, because we need a Jacobian
Okay.
du dv. So that's the first temptation overcome. The second temptation is to replace this immediately by v and by u. That might work, but only if v and u are positive. Otherwise, you might need an absolute value. So it certainly would be true to have an absolute value. You may need to deal with minuses. Hopefully not, but we shall see. And the other thing we need to deal with is where these bounds go from. So let's worry about the bounds for a second. Okay, x, y is u squared. And you see that u squared starts at 1 and goes up to 4. Now, x is u over v, y is uv, x and y are both in the first quadrant. So u and v are both positive. Actually, they could both be negative and it would still work, but that would just be silly. So actually, I think we'll take care to say that u and v are both positive. If you also allow u and v to be negative, you will get another copy of the same thing, as long as they're both negative. If one of them's negative and one of them's positive, you're over here. Or you're over here. Actually, no, that's not true. If one of them's positive and one of them's negative, you're actually over here. I take it back, because both x and y will be negative. That's the third quadrant. All right, so u squared goes from 1 to 4. And u is positive. So u goes from 1 to 2. And how about v? Well, v squared is y over x. And when y equals x, this means v squared equals 1. Whereas when y equals 4x, y over x is 4, so v squared equals 4. And hallelujah, v also goes from 1 to 2. So actually, this is a rectangle, believe it or not, in the new coordinates. And that answers your question from before, in a way. How nasty is this region in xy coordinates? It's a real mess. It's much nicer in the uv coordinates. It's just 1 to 2 cross 1 to... Yeah, you'd have to separate it. It's just horrible, horrible. So don't even worry about that. Okay, so now we just need to work out the Jacobian. Okay, now I know v and u are positive. I can replace this by v and this by u. So I need to work out the Jacobian. Because I've only got 1 minute left, I'm just going to do it up here. So I have x, I'll just repeat it, is u over v, y is uv. So the Jacobian is dx du is 1 over v, dx dv is negative u over v squared. dy du is v, and dy dv is u. This is equal to u over v plus u over v squared times v. So it's 2u over v. There's the Jacobian computation. So this integral becomes the integral from 1 to 2, the integral from 1 to 2, v plus u times the absolute value of the Jacobian, 2u over v, but we don't need the absolute value here because they're both positive. So no absolute value needed. U and v are positive. du dv. Now that's an integral that you can just work out. If I had more than 0 minutes left, I would do it, but that's the integral, okay? So the point of the Jacobian thing is it's just like a substitution. You have to change all of the xy's, or xyz's as the case may be, into uv's, or uvw. You have to change the dx dy into the Jacobian, and you have to times du dv, and you have to pay special attention to the region. No, once you get the answer, you've got the answer. Just like in a single variable integral, if you change the bounds as well, then you don't have to go back. So, without further ado, happy Thanksgiving to you all. And next week, we're on.